Hello, and in today's lesson we're going to determine a value for the Hubble constant, and that will allow us to determine how fast the universe is expanding, how old it is, and the distance to some nearby galaxies. When Edwin Hubble first started imaging galaxies, he was able to record two quantities. One was the recessional velocity of a galaxy, that's how fast it's moving directly away from the Earth, and also the distance to that galaxy. And with the data he obtained, he plotted the recessional velocity against distance, and he found that he got what he thought was a straight line. There was a lot of uncertainty in this data, but over time, as we've been able to get data from galaxies further and further away, it's become clear that this is a line, and the gradient of that line is what we call the Hubble constant. So what we're going to do today is try and obtain some data, plot them on the same axes, and see if we can get a value for h0. What we're going to do is take some images and spectral data from 9 galaxies, and once we've recorded that data, we're going to plot it on an Excel spreadsheet, and that spreadsheet has automatically been designed to calculate the gradient for you, so it should be quite quick once you've got your data. I would suggest the first thing you do is draw this table now, and then you'll be ready to record your data quickly. So the first thing we're going to do is look at how we calculate the distance to a galaxy. The idea is that there is, by measuring the angular size of a galaxy, and knowing something about the size of the galaxy itself, its diameter in this case, we can work out the distance here. There are some units which I need to quickly explain. One of them is labelled MPC. You'll see that this galaxy has a diameter of 0.01 MPC. MPC stands for megaparsec, and parsec is a unit of distance, and we write parsec just as PC. Now 1 PC is 3.26 light years, so it's greater than light year. A megaparsec is a million parsecs, so it's considerably further. In this activity, we are going to assume that all of the galaxies that we look at are the same diameter, so 0.01 megaparsecs, and that's about 30,000 light years. There are plenty of galaxies bigger than that, but these are the ones we'll be using. Now, the way that we're going to obtain the distance to the galaxy is that we're going to measure the distance from one edge of the galaxy to the other. So we're effectively going to measure the diameter in millimeters. And the spreadsheet has been set up so that it will automatically calculate the distance to the galaxy from this one measurement. So for all 9 galaxies, you just need to have the number of millimeters across the length parallel to the ruler. So in the table, I've already populated galaxy 2 with 10 millimeters, and basically just go through the rest of the the other 8 galaxies and measure those individually. There's a ruler being placed alongside each one, so you don't have to actually get a ruler itself. Calculating the recession velocity of a galaxy, well, remember from your work on the Doppler equation, we've got something called an observed wavelength and a rest wavelength. If we subtract the rest wavelength from the observed wavelength, we get what's called delta lambda, and we can then say that delta lambda over lambda is the same as V divided by C. So how are we going to actually obtain this data? Well, first of all, we've been given some spectral data, an emission line for oxygen in the lab, and this particular line occurs at 372.7 nanometers. If you look at the same line from all of the other galaxies, you'll notice that it has moved. Let's have a look and see what it looks like from another galaxy. This is galaxy 2, And the same line in this galaxy is at a slightly different position. Now, the way to do this, the way to find out exactly where it is you'll notice that a scale has been placed on the spectral information, and the 400 nanometers has been lined up with 5 centimeters, and the 500 nanometers has been lined up with 10. So that means there are 50 millimeters for every 100 nanometers. So 1 millimeter represents 2 nanometers. So you should be able to work out the position of this line in nanometers. And then what you do is record that value in your table. Okay, so 2 sets of data. One is the galaxy size and one is the observed wavelength. Once you've recorded all that data, then there is a spreadsheet in the VLE lesson which has been set up for you so that only the yellow sections are where you add your data. That's the data from your table, and the spreadsheet will automatically plot those data points and give you a gradient for that line, and that value will represent the best estimate of the Hubble constant from your data. Okay, from the value of the Hubble constant, you can then calculate the age of the universe. Depends what your value is, depending on how you read your data, but what we can say is that the Hubble constant is going to be measured in velocity divided by distance, and that's why we've got this sort of slightly strange looking unit, meters per second per megaparsec. Now, a megaparsec is given down here as a number of meters, so by converting your value of the gradient into speed divided by distance in SI units, you can get a value for the Hubble constant in per second. Now, this value for 70,000 comes out at 2.26 times 10 to the minus 18. You'll get something slightly different because your data will be slightly different that you read from the galaxy data and the size information. But once you've got this value, you can then calculate the age of the universe from 1 divided by the Hubble constant. So what is that in years? How does that compare? And you can open up this spreadsheet to find out the value that's most recently been determined and compare that with your own. Okay.